Deep inside a cryogenic freezer, chilling near absolute zero, a delicate quantum state hangs in complete, dark isolation. From the moment a computation begins, a classical supercomputer outside the freezer must receive error data, process it, and return a precise correction pulse. It has exactly 3 microseconds to complete this round trip. If that correction pulse arrives even a fraction of a microsecond late, the quantum state collapses. The entire calculation is destroyed. Running a quantum system is a mechanical race against the speed of light. Early expectations for a swift quantum revolution through noisy intermediate-scale quantum devices hit the wall of physical reality. Qubits are fabricated from fragile materials. When exposed to microscopic environmental noise, they experience parameter drift and their states degrade in tens of milliseconds. In the 1940s, engineers battled constant thermal and electrical stress as early machines routinely melted their own vacuum tubes. The hardware was unreliable. Today's physicists face the same problem. Building a functional quantum computer requires bolting it to a massive classical supercomputer, dedicated entirely to managing its fragile physics. The data generated by a dying qubit must physically travel out of the cryogenic isolation chamber and across the room into a classical server rack. Standard copper wiring creates a transmission bottleneck. A round trip here takes over 3.5 microseconds, exceeding the quantum state's survival window. To close this gap, engineers deploy a low-latency interconnect known as NVQLink. This dedicated hardware bypasses standard protocols. NVQLink represents a physical engineering requirement, raw hardware plumbing built to move analog signals at the mechanical limit of electron flow. No matter how fast a decoding algorithm runs, without this physical pipeline, error correction fails before the math begins. Pacing quickens. Even if the data arrives on time, the system faces an immediate secondary bottleneck. The quantum machine spits out syndrome data, a flood of specific physical error locations that must be tracked simultaneously. When this swarm enters standard error-matching algorithms on a CPU, the node is immediately overwhelmed. Transmission speed satisfies the latency budget, but the processing bandwidth remains insufficient. The system routes data through an Ising decoder living on an NVIDIA GPU. This decoder utilizes a three-dimensional convolutional neural network. The neural network handles the initial decoding. It receives the raw error swarm, compressing the data in parallel to strip out noise. This sparsified data returns to the CPU. The standard algorithm now easily calculates the fix and fires the correction pulse. This specific AI implementation serves as a high-throughput data filter designed to satisfy the 3-microsecond latency budget. Beyond real-time error correction, the daily maintenance of a quantum processor requires immense physical labor. Tuning a single machine takes human physicists days of manual calibration. Technicians spend hours staring at two-dimensional calibration graphs, interpreting microscopic variations in noise to adjust the system. That manual observation is now being offloaded to a 35 billion parameter vision language model. The AI looks at the plots instead of a human. The model interprets the noise variations and calibrates the hardware autonomously, operating the laboratory on its own. Open-source architectures like CUDA-Q provide the direct infrastructure for these automated workflows. The documentation for deploying them is linked below. Current architectural trends show the quantum computer functioning as a specialized coprocessor, integrated directly into classical data center racks. The engineering effort required to stabilize these qubits mirrors the struggles of the 1940s, when technicians fought to keep massive racks of vacuum tubes from melting under their own heat. The physical demands remain consistent. We are waging the same fight on a subatomic scale. The history of computing is a constant war against physical limits. The quantum era is the next battlefield.